Let's have a look at the precision approaches for landing. This is a very important topic in air transportation because landing is the most critical phase of the flight of an aircraft, and we always want the aircraft to land safely and securely every time. Takeoff occurs from ground to air, so the pilots are aware of the situation on the ground because they can feel it. But when you transition from air to the land, the feel of the pilots is much lower, and therefore it is very important to provide support and help to the pilot when they come in for landing, and that is obtained by using precision approaches where guidance is provided to the pilot, and we will see how it is actually incorporated. First, let us start with the definition of precision approach. A precision approach is an approved descent procedure using a navigation facility that is aligned with a runway where the glide slope information is provided. So, notice that only the glide slope information is sufficient for you to be classified as a precision approach, along with some way through which you can align with the runway. For landing, several precision instruments are used, such as the instrument landing system, the microwave landing system, the transponder landing system, precision approach radar, and the ground based augmentation system GBAS. All of these come under the precision instruments for landing, and we will look at all of them today one by one. To start with, let us look at the ILS, or the instrument landing system, the most commonly used system worldwide to provide precision guidance to the aircraft at landing. This is very much accurate and dependable means of navigating to a runway at landing. Two types of guidance are provided in an ILS system: lateral guidance, so that you can align with the runway, and vertical guidance, so that your approach angle is appropriate, and if you follow the guidance provided, you will touch down at the runway precisely at the point where you are expected to touch down. The history of ILS system is very interesting. The system was first tested somewhere in 1929. It was implemented 9 years later in 1938 for the first time, and in 1941 6 systems were approved worldwide before it was launched globally, and today almost all major airports, or I should say almost all runways of major airports at both the ends, generally have a very sophisticated and calibrated instrument landing system. Here is an overview of the instrument landing system with its various components. There is a localizer aerial, and there is a glide slope indicator, and there are these 3 markers: the outer, the middle, and the inner marker. Let us have a look at these components in some detail. The first and the important aspect of an ILS system are the components which are localizer, transmitter, and receiver, which is mounted at one end of the runway, as you can see, the far end of the runway. Then you have the glide slope transmitter and receiver, which is mounted generally on one side of the runway. 3 markers co-located with a non-directional beacon, the outer marker, and you have the approach lighting system. All of these constitute the ILS system, and we will look at now all of these one by one. First, let us look at the localizer, transmitter and receiver called as a transceiver. This, as I mentioned, is generally at the far end of the runway, aligned with the runway center line. It is a VHF based transmitter. It provides horizontal guidance to the aircraft. Okay, we say it gives the horizontal azimuth. It's like a VOR, but it is 4 times more sensitive than a VOR. The next component is a glide slope transceiver, which is a glide slope transmitter and receiver. This provides the vertical azimuth, and that helps in automatic landing also. The glide slope transceiver is a UHF component providing vertical guidance, mounted generally on one side, the left side of the runway at which you are approaching. Then we have the 3 markers which provide to the pilot the range information. That means you get a visual and an oral signature of how far you are. Okay. Sometimes we co-locate them with a DME or a distance measuring equipment, right. The outer marker is normally located around 11 kilometers or 6 nautical miles from the end of the runway. The middle marker is located approximately half nautical mile or 1 kilometer from the runway end, and the inner marker, which sometimes is omitted, is 60 meters from the runway end or about 100 feet. Notice the 3 colors: blue, amber and white. These colors correspond to the colors of the instrument in the cockpit, which give a visual light signal: blue light, orange light or amber light and white light, as well as oral signals of different frequency and pitch. Let us look at the categories of ILS system. So, before we define the categories, we need to understand the parameter which is used to identify the categories, and that parameter is the RVR or the runway visual range. Definition: the runway visual range is the maximum distance in the direction of the takeoff or landing at which the runway or the specified light or markers delineating it can be seen from a height corresponding to the average eye level of pilots at touchdown. So, when we say RVR 24, we mean that the runway visual range is 2400 feet. When we say R36 400 feet D, what we mean is that the runway visual range for runway 36 is 400 feet and it is decreasing with time. How do you measure the RVR? To measure the RVR, we use an instrument called as a transmissometer. A transmissometer is an instrument that is located alongside the runway. It has a large light, it has a light source and a photoelectric cell receiver. It senses the reduction in the light level, dim light, bright light. The photoelectric cell receiver is used to detect the level. RVR can be measured only till about 6000 feet, and usually you measure RVR at 2 locations: the touchdown point or the point where the pilot is supposed to touch the aircraft down, called as the alpha point, and then there is a midway point called as a bravo point, which is approximately at the middle of the runway length. At these 2 points we measure the RVR. Another concept that we need to understand when we look at the ILS categorization is decision height. The decision height is the specified height in precision approach at which a missed approach must be initiated if the required visual reference to continue approach has not been required. So, when the pilot is along the approach to land, there is a particular height at which the pilot confirms whether the runway is visually seen or not. If it is not seen, the pilot is supposed to execute a missed approach. Now, what is a missed approach? Let us quickly have a look. In a missed approach, the aircraft descends, reaches a decision height. At that particular height, because runway is not visible, therefore, it aborts the landing, and hence it is called as a missed approach. The decision height serves specific purposes. It allows the pilot sufficient time to safely reconfigure the aircraft to climb in case you are not able to visually acquire the runway at that particular point, then it is better not to continue. It allows the pilots to execute the missed approach procedures while avoiding terrains and obstacles. So, when you look at these two parameters, the decision height and the runway visual range, these two parameters are utilized to decide the category of the ILS system. You have ILS systems of category 1, 2 and 3, and category 3 is subcategorized as 3A, 3B and 3C. So, in short, you have 5 categories of ILS system based on the value of the runway visual range RVR and the decision height on the altimeter or DH. Category 1 is applicable to those airports where the RVR is 18,000 feet or visibility of 2625 feet and the decision height is 200 feet or 60 meters. So, the aircraft can come to as low as 200 feet above the runway, and at that point, if either the RVR is less than 1800 or the visibility is less than 2625 feet, the pilot is supposed to execute a missed approach, because this system is not capable to handle precision beyond this level. In category 2, the runway visual range reduces to 1150 feet or 350 meters and the decision height reduces to 100 feet or 30 meters. So, you are lower compared to the previous decision height, you are from 200 feet you are 100 feet, and at that particular altitude, if you are not able to acquire the runway or if the RVR is less than 1150 feet, then you are not supposed to execute a category 2 approach, you have to do a missed approach. Category 3A, the lowest of category 3, reduces the runway visual range to 655 feet or 200 meters, but the decision height remains the same, that is 30 meters or 100 feet. Category 3B reduces the RVR to only 50 meters at a height of 50 feet. So, now in category 3B, both the decision height has been reduced and the RVR at that height is also reduced. So, even if you bring the aircraft to 15 feet above the runway surface and if your visibility or RVR is less than 165 feet, then even CAT 3B is not enough, you have to abort the landing. And finally, we have category 3C, where there is no requirement for RVR or for decision height. That means it can even be a blind landing. The aircraft can be brought to the airport with the pilot not seeing anything till the aircraft touches down. This is the most precise category of the ILS system, which is there only at very few airports in the world, because it is very difficult to maintain the facilities, calibrating them, keeping them working, ensuring their precision, ensuring that the pilots are also trained to able to execute those kind of approaches. So, it is a very expensive exercise for the airline as well as for the airport, but certain airports, mostly in North Canada, or in areas where you have a huge issue with the weather throughout the year, you are forcibly required to install category 3C in order to operate. So, here is a table that shows all categories in one shot. You can notice that as we go down from category 1 to 2 to 3A, 3B, 3C, the RVR generally reduces from 550 meters to 50 meters and nil, and the decision height reduces from 60 meters to 30 meters to 15 meters to nil. Now, let us look at the components little bit more detail. Okay. This is the localizer. I have already mentioned to you what it is and what its purpose is. Localizer transmitter basically is an antenna array which is located beyond the departure end of the runway, and there can be several pairs of directional antennae in the localizer antenna. It transmits two VHF signals. These are transmitted transmitted by co-located antennae, but they are separated. Okay. The carrier frequency of this transmission is between 108 megahertz to 111.975 megahertz. One of the beams is modulated at 90 hertz and the other is modulated at 150 hertz. So, each antenna transmits a narrow beam, okay, on left side and the right side with some overlap. The beam width is around 5 degrees and therefore, the beam thickness increases with distance. It has at the runway threshold, the intersection is about 700 feet, the beam width is 700 feet and 1 mile width at 10 nautical miles from the runway. Here is a sketch of the localizer antenna, and here is a picture of one of the localizer antenna installed at an airport. This is at the Mena Airport in Arkansas in USA, at KMEZ Airport, runway 27. The localizer receiver is an instrument which is matching with the transmitter, but this is on board the aircraft. This is usually paired with the VOR receiver. It measures the difference in the depth of modulation of the two signals. As I mentioned, there are two signals 90 and 150 hertz, and they are having an interception. So, this instrument on board measures the difference in the depth of modulation. The DDM depends on the position of the approaching aircraft from the center line. Okay. So, when DDM is 0, it means you are exactly at the center line, and the horizontal situation indicator or the course deviation indicator on the aircraft indicates any offsets between the two. So, with that you are able to align yourself with the runway center line. There is a reception range limit. So, the reception range of a localizer antenna is 18 nautical miles if within a 10-degree track and 10 nautical miles if within a 35-degree track. So, this much is enough for us to know about the localizer receiver. Let us now look at the glide path antenna, which as I mentioned is a UHF component mounted on one side of the runway and provides vertical guidance. This is a ground based UHF transmitter and airborne receiver on the aircraft. The carrier frequency is between 329.3 and 335 megahertz. Okay. The center line is arranged to define a glide slope of generally 3 degrees, but this number can change from airport to airport. 3 degrees is the average value or the normal value that we use, but it could be more or less at an airport depending on the presence of obstacles in and around the airport and also during the approach path. So, in some airports you may come at a larger angle of glide slope. For example, there is an airport in the middle of the city of London called as the London City Airport, LCY. At that airport the glide slope is 5.5 degree. Similarly, at some other airports it may be 2.8 degrees, 3.1 degrees depending on the local geography. This particular glide slope is monitored with a very small tolerance of plus or minus half degree. Okay. As I mentioned, this is sighted on one side of the runway touchdown zone or on the generally on the left hand side as the pilot seizes. The offset could be about 500 feet from the runway center line and around 1000 feet down the runway from the threshold. That is where it is normally located. These two frequencies of the localizer and the glide slope, they are paired because we want to tune the receiver, so that only one selection is required to tune both the receivers. Glide slope path signal basically are two overlapping beams, one at 190 hertz and 150 hertz like the localizer, and they are radiated primarily along the approach track. Okay. The thickness of the overlap area is about 1.4 degrees, okay. And as you can see, the thickness varies from location to location. It is 1500 feet at 10 nautical miles, 150 feet at 1 nautical miles and less than 1 feet at the touchdown point. Now we look at the marker beacons which are there for the outer, inner and middle marker. These markers provide a distance information to the pilot from the runway, how far you are from the runway, and they are used by identifying predetermined points along the approach track of the aircraft. These are low power transmitters operating at 75 megahertz. They radiate an elliptical beam upwards from the ground. At around 1000 feet height, the length and width of this beam are 2400 and 4200 feet respectively. There are three markers as I mentioned, 11 kilometers, 1 kilometers and about 100 meters from the runway edge. The outer marker can be at around 6 nautical miles from the runway threshold with a 20 to 50 degree of extended from runway center line. This is the final approach fix for non-precision approach. The intersect glide slopes, it intersects the glide slope at 1400 feet elevation, and when the aircraft crosses the outer marker, the pilot gets a blue light flickering on the instrument board and an oral signal. This outer marker is normally co-located with DME if possible, and sometimes it is replaced by a non-directional beacon also. The middle marker is located about 1 kilometer or 0.6 nautical miles from the threshold to the extended runway center line. It crosses the glide slope at 250 to 100 feet above the runway elevation. This is using an amber light. So, when the aircraft crosses the middle marker, the pilot gets an amber light and an oral signal when it passes. This particular point is near the missed approach point for ILS category 1 approach. So, when the pilot comes in to land in ILS category 1, when it reaches the middle marker, that is the point where normally the pilot decides whether to continue or to miss the approach. The inner marker is very much near from the runway threshold, around 60 meters or 100 feet from the runway threshold. It indicates the imminence of arrival of the runway at low visibility conditions because it is almost there. What is 60 meters? It will happen in a few seconds. This particular marker is only installed in category 2 and 3 ILS systems. It is not installed in category 1 systems, and this represents the aircraft position as it reaches the Cat 2 minima. Just like the middle marker was corresponding to the Cat 1 minima, the inner marker corresponds to the Cat 2 minima. Okay? And in the cockpit, there will be a white lamp that flashes along with a audio warning. So, this is how the pilots get an indication about their approach. There are lighting systems which are supporting the information available by the ILS. They are on the approach end of the runway and they extend outward from the runway end. They consist of a series of light bars and strobe lights or a combination of these two, and they are provided in the instrument approach procedures. They allow the pilot to visually identify the runway environment once it arrives at a prescribed point on the approach. So, you get a aerial information while you are still in the air, you get this information. You can activate the approach lighting system on board by firing some instrument, or it can be also operated by the ATC upon request. So, at some small airports in the remote areas, the pilot can transmit a particular frequency and the approach lighting system will switch on. These are typical approach lighting systems. You can see there are these lights which flash and strobe. This is another example. You can see that the stopway is marked with red colored light. There is a caution zone of yellow color which tells the pilot that you are nearing the runway end, and there are some other marks, and at some places there is a supplementary approach lights also. So, all these give a visual indication of the runway to the pilot. An interesting variation is the remotely operated approach light system, which is also called as pilot controlled or pilot activated lighting, PCL or PAL. Another name for it is aircraft radio control of aerodrome lighting or ARCAL. The pilot can turn the video signal by a signal. The pilot can turn it on using a radio signal, and when the signal is received, the approach lights, the runway end edge lights and the taxiway lights all come into play. Then there are three settings. There is a low intensity setting which have 3 clicks in less than 7 seconds. There is a medium intensity setting and there is a high intensity setting. This again depends upon the kind of approach the pilot is executing, kind of the aircraft that it is operating, and the weather conditions also. After a 15-minute operation, these lights normally turn down. After a 15-minute operation, these lights normally turn down. Okay. Now, ILS system has got some severe limitations. It lowers the throughput of landing aircraft because all aircraft have to come now straight in. They have to start aligning with the runway many kilometers beforehand, and they have to come at a constant descent angle. Because of this, the rate at which the aircraft can arrive at the airport reduces. Okay. Then the instruments are based on VHF, UHF transmission receival. So, there can be sensitivity of the localizer systems because of obstructions on the signal broadcast area or because of the presence of large buildings or hangars. The signals can get reflected and cause confusion. Similarly, the glide slope system is also very sensitive. It is sensitive to the terrain in front of the antenna. If the terrain is very uneven, there are more reflections, and these reflections give a confused signal to the pilot. The glide slope becomes uneven. An ILS system is expensive to set up, expensive to maintain, and expensive to keep upgrading, because you have to meet certain sighting criteria and handle the complexity of the antennae. So, to remove these shortcomings, a more advanced system called as a microwave landing system was proposed. This is designed to replace ILS after 2010, but it did not happen. Okay. ILS systems limitations include lesser number of channels because the frequency band is very small. This has got wider signal selection of channels. It gives you very good performance under all weather. It gives you a smaller airport footprint. It also allows you to approach from side instead of coming in straight. So, it gives a much wider vertical and horizontal capture angles. Okay. But it did not gain popularity for two reasons. One reason is that the ILS system was already in place and all the airports had already invested large amounts of money in setting up and maintaining the ILS system. Putting a new system would mean repeating those expenditures, and by that time the MLS system actually was proven, the availability of GPS and wide area augmented systems based on GPS and satellites, they were made available. So, it did not gain popularity. This is one example of a system which was technically much better than ILS, but it could not be implemented because of commercial considerations and because of the availability of a much better system. You can see the coverage volume of ILS of MLS system here. You can see that it allows approaches from the sides, so it can definitely increase the throughput of the airport. Okay. It also has much larger coverage in the elevation as compared to the ILS system. One more system is called as the transponder landing system or TLS. This is the all-weather precision landing system for precision approach, which uses existing airborne transponder and the ILS equipment, and it interrogates all transponders within 100 nautical miles, and therefore it helps you to avoid any interference with the other aircraft. It determines the position of the aircraft using 3 antenna signals: horizontal, vertical and trilateration. It provides you real time guidance on radar scope similar to the secondary surveillance radar. Okay. So, this is used where ILS is not available or S-band satellite based navigation system is not possible. It is used when there are short runways, where there are obstacles, constraints because of real estate, because of water bodies near the airport, at airfields located near Arctic Circle or equator, where other systems do not work very efficiently, this can be used. And finally, we have another system which is used mainly by the military, called as the precision approach radar system. This is again using ground based controllers, but these controllers are now completely mobile. Okay. This is also called as the ground controlled approach or GCA. It is a unique radar display with 2 separate traces. The upper trace gives you the elevation and the lower trace gives you the azimuth. So, with that you are able to guide an aircraft precisely when it comes into land. It is normally used by military aviation, especially by Navy. Here is an example of a precision approach radar system installed in a military airfield in Germany. But these systems can also be made mobile. They can be mounted on trucks which can be used to create a PSR at any remote location after spending some time in training. And finally, we look at GBAS, which is the ground based augmentation system. With the advent of GPS and the GNSS satellites, we were able to use this all weather landing system called as GBAS. This gives you information with real time differential correction of signals. So, there are local reference receivers which are connected to the central data server, and the correction message is sent via a VHF data link. So, GBS approach service type C, that is called as GAST-C, currently used only for ILS Cat-1 minima. But more and more research, more and more trials are happening, so that the GBAS systems can be used for higher values of ILS also. There is something called as GAS-D, which will allow permit landing with Cat-3 minima. Okay. And then the aim is to have a single receiver to replace many navigational equipment receivers, such as instead of having ILS at each end, NDB, DME, VOR, MLS, GPS, instead of that there will be a single receiver which will replace all of them. This was earlier called as local area augmentation system by the FAA, but now the name is GBAS, ground based augmentation system. Here is an overview of GBAS system. You can see it talks to the satellites and gets information, and with that you can get precise location of where you are. Thank you for your attention.